In this video, we're going to look at derivatives of logarithmic and exponential functions. So if we want to take the derivative of e to the x, it's going to be e to the x. The derivative of the ln function, ln of x, is going to be 1 over x. The derivative of b to the x, where b is any base except e, is going to be b to the x times the ln of b. And the derivative of the log base b of x is going to be 1 over x times 1 over ln of b. So let's look at a few examples. Let's say we want to take the derivative of ln of x cubed plus 3x minus 4. So this is going to be a chain rule problem. So let's let u be that inside function. So du is the derivative of that. So then if we were to rewrite, we have ln of u, and the derivative of the ln is 1 over u times du. And then if we substitute back in, it's going to be 1 over x cubed plus 3x minus 4 times du, which is the derivative of the top. And I'm just going to rewrite this. So this is, the derivative is 3x squared plus 3 all over x cubed plus 3x minus 4. Let's say we want to take the derivative of e to the 7x. U is going to be 7x. Du is 7. So when we rewrite, this is e to the u, and the derivative of e to the u is e to the u times du. And when we substitute in, e to the 7x times 7. So we could say y prime equals 7e to the 7x. And let's do just a couple more. No, looks like I didn't lasso everything. Let's say we have y equals 3 to the x. So our rule for that, the derivative, is going to be 3 to the x times ln of 3. And then let's say we want to take the derivative of the log base 4 of 2x squared minus 1. So we're going to use this rule. U is that argument 2x squared minus 1. Du is 4x. So when we rewrite this, this is the log base 4 of u. And the derivative of that is 1 over u times 1 over the ln of 4 times du. And then when we substitute back in, we're going to have 1 over u, which is 2x squared minus 1, times 1 over the ln of 4 times du, and our derivative is 4x. Now I'm just going to clean this up. So y prime equals 4x over ln of 4 times 2x squared minus 1. The last thing we're going to talk about is how can we use logarithms to help us take the derivatives of some things. Anytime your x is in the exponent, you're going to have to use logarithmic differentiation. So let's look at an easier one. Suppose we want to take the derivative of x to the x. We know as long as we do the same thing to both sides of the equation, it's going to be a legal move in math. So let's take the logarithm of both sides. The reason we would want to do that is because we have a property that says we can pull that exponent to the front. So that right-hand side can be rewritten as x times ln of x. And then now we're in a form where we can take a derivative. We don't have a derivative rule for this, but we do have a derivative rule for this because this is really just a product rule. And then that left-hand side is going to be implicit differentiation. The ln of y, when I take the derivative, is going to be 1 over y times y prime. This is a product rule, so it's first times derivative of the second plus second times the derivative of the first. And then I'm going to clean this up. And then I'm going to get y prime by itself. That's always the goal. So to do that, I'm going to have to multiply both sides by y. And then remember, we have a substitution for y. We said in the beginning y was equal to x to the x. So there's the derivative of x to the x. It's 1 plus ln of x times x to the x. We can use that same concept on this one. Okay, anytime you have an x in the exponent, you have to use, well, if you have x's in the base and in the exponent, you have to use this property. This is one of our tricks. So we're going to take the ln of both sides. That's going to allow us to bring that exponent to the front. The derivative of the right-hand side is going to be, sorry, the left-hand side is going to be y prime over y. It's 1 over u times du. We have to show implicit differentiation here. That's why we have that y prime. This is a product rule. Product rule says it's the first function times the derivative of the second. This is going to be a u substitution. U is 2x to the fourth plus 1, and the derivative of u is 8x cubed. So there's my du over u, plus the second times derivative of first. The derivative of the tangent is secant squared. And then to get y prime by itself, we're going to multiply both sides by y. So we have 8x cubed tangent of x over 2x to the fourth plus 1 plus ln of 2x to the fourth plus 1 times secant squared of x, and all of this is multiplied by y. And y was originally ln of 2x to the fourth plus 1 raised to the tangent of x. So 8x cubed tan x over 2x to the fourth plus 1 plus ln of 2x to the fourth plus 1. Multiply that by secant squared of x. Multiply all that by y, which is 2x to the fourth plus 1 raised to the tangent of x. So there's our derivative. Now what's nice is we could use a logarithmic differentiation to do an expansion using log properties that help us take derivatives and to make them look a little bit nicer. So let's say we want to take the derivative of this guy. This guy's a mess, right? Because if you think about everything that's going on, we have a quotient rule. Okay, when I take the derivative of the top, that's going to be a chain rule. When I take the derivative of the bottom, I'm going to have a chain rule here, and then it's also a product rule. So let's see if we can take the log of both sides and make this a little bit easier to deal with. I'm going to expand that right-hand side. So that division means I would take the ln of the top of the fraction and subtract the ln of the bottom of the fraction. And then we can expand this further. This product means this is going to be the ln of x plus the ln of the square root of 2x plus 1 minus, we're going to have the ln of e to the x plus ln of sine cubed of x. And then let's deal with these exponents. We could pull these exponents to the front. That square root is the same thing as a 1/2. So this is x ln of e plus 3 ln of sine of x. And then I'm going to simplify just a little bit more. We know ln of e is 1. I'm going to distribute that negative. And I'm going to distribute that negative here. ln, and remember this is sine of x. So this guy is equivalent to this guy. And now this is going to be really easy for us to take the derivative of. We can just take the derivative of each piece. So we're going to have y prime over y. Remember, this is implicit differentiation. It's equal to 1 over x plus 1/2. This is a chain rule, so it's du, which is going to be 2, over u, which is 2x plus 1. Derivative of negative x is a negative 1. Same thing here. This is going to be du, derivative of sine is cosine, over u. So we have y prime over y equals 1 over x plus 1 over 2x plus 1 minus 1 minus 3, and we know cosine over sine is cotan. So y prime is equal to 1 over x plus 1 over 2x plus 1 minus 3 cotan of x. All that's multiplied by y. And then originally y was x square root 2x plus 1 over e to the x sine cubed of x. So there's my derivative. And that would be really easy for us to plug numbers in if we needed to evaluate.